It's like, hello, my name is Mrs. Erickson, and I believe water is not. No, I'm just kidding.
Okay, take 2. Okay, did it just get darker?
Mm-hmm.
Yeah.
When you started recording, it went darker.
Weird. All right. Anyways, chapter 2 is our chemistry chapter. So like I said, we're going to deal with atoms and then the subatomic particles. Talk about oxidation, reduction, reactions. We call them redox reactions. We're also going to talk about acids and bases and the properties of water. And you'll kind of explore those properties of water in this week's lab. So, big chapter, lots of slides. I did post it to the Google Classroom. So, all right. So, learning outcomes, obviously know the structure of an atom, how it's made up of protons, neutrons, the nucleus, and the electrons on the outside orbit in it. Differentiate between atomic number and atomic mass. Understand the importance between ions and isotopes. So it's just a lot of chemistry vocab in this. Understand that protons actually give the chemical identity of a given element, but then the properties are responsible by the electrons. Talk about reduction, oxidation reactions. How water can spontaneously dissociate. So notice it's H plus and O minus. Well, you form together, you get water, but sometimes water kind of just dissociates as to ions, and then they can rebond. So we'll talk about buffering systems, elements and molecules. Talk about the various bonds, covalent bonds, non-polar covalent bonds. Why is water the essence of life as we know it? And then finally wrap it up with acids and bases. So it's probably going to take us to 2 days here. But a little introduction. So whenever I do lectures and you see a different colored background, it's kind of like a little side trip. Kind of like another story with science. So we're going to learn about things, and then we're going to come back to the story and then see how the story develops. And so chapter 1, I told you about spontaneous generation. How people, observed the world around them and made these conclusions, that flies come from meat because you set out some meat. A couple days later, maggots, flies. Okay? So this idea of living organisms coming from non-living items. But here's a question, actually a thought for you. But for life to exist now, it must have occurred at least once, because Earth at one point did not have life. And then it started to build molecules, and then these molecules underwent chemical reactions, and then from there we started life. So ultimate mother of all questions, how did life begin? So in this chapter, we'll examine a hypothesis called chemical evolution, which basically says or proposes that in Earth's early history, simple chemical compounds in the atmosphere and ocean combined to form larger, more complex molecules. And then as a result, the chemistry of our oceans and atmospheres changed over time. So like right now, our atmosphere is 78% nitrogen and about 22% oxygen, but that wasn't always the case. Okay, at one point, there was hardly any oxygen on planet Earth. So, we'll talk about how that's changed over time. More complicated compounds produced and then continued and then eventually led to this origin of life. So then this is just a hypothesis that one of these complex compounds was able to make a copy of itself or self-replicate, because that's one of the characteristics of life, is that organisms have DNA, and this molecule has to be able to replicate so it can be passed on to its daughter cells. And then this molecule obviously multiplied through the process of evolution by natural selection, took over. So whenever you see N.S, that means natural selection. And then it switched from chemical evolution to biological evolution. So it's kind of a crazy idea. It's a hypothesis. So we're going to see what kind of evidence we can dig up that can support this. So 12.5 billion years ago, enormous explosion marked the beginning of the universe. This number is tentative. I've heard 14. Okay, your book states 12. The process of star building and planetary formation led to the formation of Earth about 4.5 billion years ago. So you may remember from Earth science. Did I have you guys as Earth science? I think I did.
Yeah, because we had to do the rock things.
Yes. We talked a little bit about planetary formation, how gas, dust, rocks started to combine and form the inner planets, and then the gases, the lighter stuff, formed our outer planets. So we're in the inner planet. Ancient Greeks recognized that larger things are built of smaller parts. They literally thought, okay, if I take this piece of paper and I rip it in half, and I take one half of that paper and I rip it in half again. And I just keep ripping this piece of paper in half. Eventually, I'm going to get to what paper is made up of. Okay, so then this is the idea of where the atom came up. What is the world made up of? So to understand how living systems are assembled, we have to talk about the atomic structure and how atoms have this ability to link together to form molecules, and then how those molecules form cells, and then cells form tissues, and tissues to organs, and organs to organ systems, and organisms. So study of life on Earth begins with physics and chemistry. Like I said, ancient Earth, totally different place than what it was today. So again, with the formation of the planets, we've used computer simulations to model those conditions that have led to the development of Earth. And we've also looked at how other planets far away are being created elsewhere in the universe. So we kind of have a pretty good idea about how planets form. We call this the condensation theory. So there's that term, theory. We accept it until we come across something that totally forces us to revise it. So young planets are still surrounded by dust, and planetesimals, basically just kind of like small rocks. And there's lots of heat being generated by these larger impacts. And this is why Earth has a molten kind of inner core, and our core is still active today. The outer layers of Earth begin to cool and started to form our crust. But because our inner core is still active, magma, which turns into lava, gases are being escaped. Those gases eventually cool in our atmosphere and then condense to form our first oceans. So a little break from the story of Earth, and let's kind of jump into the nature of atoms. So anything that takes up space and has mass is matter. So I always like to tell the cheesy joke, you guys matter. You guys take up space, you have mass, you matter. Okay. All matter is composed of extremely small particles called atoms, and now we know that the atom has subatomic particles like protons, neutrons, and electrons, and then even particles that are smaller than protons, neutrons, and electrons themselves. So we just kind of keep breaking it down. But it does include that central nucleus with electrons that orbit on the outside. We haven't really seen an atom with our naked eye. We've seen it indirectly using tunnel and microscopy. So we have Niels Bohr, kind of the guy responsible for, discovering subatomic particles. The nucleus is made up of protons that have a positive charge, and neutrons have no charge because neutron sounds like neutral. Electrons have the negative charge, and again, they are outside of the nucleus orbiting. So a few terms you need to know for your test. Okay, I cannot stress this enough. And if you want, I can give you an additional chemistry packet to kind of work through the difference between atomic number and atomic mass. All right, so the nucleus is held together by a force that works only over short subatomic distances. So you may remember magnets, okay? And opposites attract and like charges repel. So if I have a bunch of protons in my nucleus, protons have what kind of charge?
Positive.
Well, how come the neutrons stick together? Or sorry, how come the protons stick together if they're all positive? Wouldn't they repel and just split, right? You guys ever thought about that before? Or you just always accepted protons are in the middle? You just accepted.
Aren't protons and neutrons?
I know, but I'm just saying. Well, you guys have never questioned how. Okay, well, the answer responsible for that is the neutron. The neutron gives just enough space to keep those protons from repelling away from each other. Okay. Now, typically, an atom it has one electron for every proton. So if you have a positive charge and a negative charge, they're going to cancel each other out. So if you have the same number of protons and the same number of electrons, it's a neutral atom. When you start to change those numbers, then you start to get atoms called ions, which means they carry a charge with them, maybe a +1 charge or a -1 charge. So we'll talk more about that in the upcoming slides. Different atoms are defined by the number of protons. The protons is the atomic number. On the periodic table, on this periodic table, it's the black number. So all iodine atoms have 53 protons. All bromine is 35. All chlorine is 17. All carbon is 6. So the number of protons determines what type of element it will be. And so I put the little definition of an element here. Any substance that cannot be broken down to any other substance by ordinary chemical means. Okay? Chemical behavior, on the other hand, is due to how many electrons are in the outermost energy shell. So if you look at a periodic table and we look at group 1, which consists of hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, all of these guys have one valence electron in its outermost energy shell. They are highly reactive. They will react with air and water. A lot of times you have to keep it in oil so it can't interact with those stuffs, with water or air. If I look at my noble gases, which consist of helium, neon, argon, krypton, xenon, radon, these guys have a full outer energy shell, so they don't really react with anything. These guys are extremely stable. And so the whole objective of atoms is to bind with other atoms to achieve a full outer energy shell. So group 2, also another highly reactive group of elements. Beryllium, magnesium, calcium, strontium, barium, and radium. Again, they will react with water, just not as vigorously as group 1. And then we kind of skip the transition metals. So these guys have one valence electron, that's group 1. Group 2 has two valence electrons. Skip the transition metals. Hop on over to boron, aluminum, gallium, indium, and thallium. These guys all have 3. Then the next column over is 4, and 5, then 6, then 7, then 8.
Oh, 3 what again?
What?
What'd you say they have 3 what?
3 valence electrons. 3 electrons in the outermost energy shell.
Why do you skip that whole section there?
The transition metals, because they have this amazing ability to have 3 or 2 or 1 or 4. There's no set pattern for metals. Their electrons are a little bit more loose.
Why is it get negative up on the top?
Oh, I'm glad you noticed that. Okay, Herman, I'm going to move it over so you can see my periodic table, because you're probably just like, what the heck is she talking about, right? Okay, don't say anything. Just kidding. Whoop, wrong way. These kids, they just mess with my camera. I don't know what they do. Yeah, hold on. Oh, come on. It's frozen. There we go. There we go. Come on. Come on. Seriously. I feel like I'm like casting a spell.
This is how
Wingardium Leviosa.
Do you want to look at Julian's paper?
It's okay, you can laugh. Okay, zoom out now. You can do it.
Roots froze from getting away. Oh yeah.
Now just go up a little bit. All right, we're in. Oh. Okay, we're in business. Okay, here's my lovely periodic table hidden behind a door there. Okay, so I was just saying, group 1, 1 valence electron. Group 2, 2 valence electrons. Then someone said, why is there a +1, +2, +3, 4, -3, -2, -1, and then nothing? Because these guys have 1 valence electron, is it easier to just give up that 1 or gain 7 to get a full outer energy shell?
Oh,
Give it up. Okay, now let's just take a look at lithium. This 3 means how many protons? Oh, I just said the answer. That was stupid. It's got 3 protons. Okay, so if I write on the board here, 3 protons. And let's just say it's neutral. So how many electrons? 3 electrons. Now I'm going to draw lithium. The first energy level always holds 2. And then the second one and every one after that is 8. So here's my 1 lone valence electron. And we just said it's easier to give it up. Okay? So it's going to give it up.
Once you get above 4, it's close.
So now how many electrons do I have?
2.
2. But I have 3 protons. So now I have an unbalance. Think of it as a scale. So I have 3 pluses to 2 minuses, or if you do a little bit of math, 3 minus 2 means 1. There's that +1. Now I can do that to Sodium. Okay, now I gotta hold on.
Wait, is there 2 in each? Is there always 2 in the first outer shell?
Yes,
So
always.
Is that the charges then?
What?
Are those the charges?
Yes, if they're ions, that's the charge they will have.
Did you say they have an equal number of neutrons per proton?
No, that's
No.
different. Hold on.
Okay, I still these should two
Alright, I'm gonna recap this for Herman Norcross so they just could see what I'm on the board since my camera is really, really slow. So, I just drew lithium. Okay, lithium, we've determined has 3 protons and 3 electrons because it's neutral. Now, when you show lithium with its valence electrons, you usually draw a circle that represents an energy level. And 2 electrons always go in the first energy level. But I still need to draw 1 more. So then I draw a second energy level with 1 electron there. So I have 3 electrons. 1, 2, 3. Then I asked you guys, is it easier to gain 7 or give up that 1? And for energy purposes, it's a lot easier to just give that electron up. So it gives it up to whatever it's going to bind to. And as a result, we lose that energy level. And now I have a full outer energy level, but my number of electrons have changed. So now I don't have 3 anymore. I have 2. Which means my overall net charge is +1. And you can see on top of my periodic table, and you'll see it on other periodic tables, maybe if you ever use a chemistry book in Rourke's, but I don't know if you will. My class, the periodic table in the back of the book has these added to it. I told the kids too. So, +1. I can do the same thing for, let's do magnesium, just because,
What does the 8 mean? Like, you said there's always 8.
right, as 8 means it's a full outer energy level, so you can go on to the next one. It's just, it always goes 2, 8, 8, 8, and it just keeps going. Then eventually, things get really crazy with the transition metals. So I never have my kids draw electron diagrams with metals. It's just, it gets really messy. Okay, so let's quickly take a look at magnesium, okay? So Mg for magnesium. If you look at the periodic table, how many protons should it have? 12 protons and neutrons. So, why do I say neutrons? Electrons. All right, so I'm going to draw this bad boy out. Whoops, okay, I'm good. So I can hold 2 in the first one. 1, 2, so I still have to draw 10. So then I go on to the next one. So far I have 10 electrons drawn. So now I'm going to the 3rd energy level. And I'm going to draw 2. Whew. That means I need 6 more. Heck no. It's a lot easier to give those 2 up. Okay? So magnesium will give those up. We lose this outer energy level, so now we have a full 2nd energy level. That's cool. But my number of electrons change. I have 10. So then my overall net charge is +2. And then you'll notice group 2 has +2.
So do they just make it for 8? Like, is that actually how much it takes, or they just make it for the simplicity of making up the diagram in order to even it out?
Well, you're gonna learn in chemistry that energy levels, like the circles, they're not like that in real life. They actually orbit.
8 to be stupid.
Yes, they need 8 to be stable. That number we know is true,
So they made the diagram, obviously.
but the diagram is for simplicity.
I mean, like that diagram, in order to have
Oh.
it lined up at 4, 12.
Yes,
22,
Mendeleev, Moseley, and a few other scientists helped rearrange the periodic table, so there's a purpose to the way it's set up.
That all the ones in the first can have an extra proton, and then like the ones that say negative, that means they can have
No,
3
Yeah, I was
extra.
actually going to draw fluorine next, so let's look at a negative.
I mean, just like.
Wait, what about like hydrogen? If it only has 1.
Okay, hydrogen is in a class by itself. I'm glad you asked that. It does have 1 proton and 1 neutron. Actually, no, not neutron. Take that, erase that from your memory. 1 proton, it's got 1 proton, okay? So we put it in the first column, but, and it's, just as reactive. I mean, it doesn't really explode, but just for simplicity, it's got 1 electron in its outermost energy shell. So they put it in group 1, but it's not considered an alkali metal. These guys are all metals. Hydrogen is not a metal.
It's the same with like helium.
Helium is a noble gas, and they don't stick it here because again, it's not a metal, but it has a full outer energy shell. Because the first level can hold how many? Two. So it's full.
So it can't really get rid of any or gain any.
Right. Helium is non-reactive in most cases. I think the only noble gas that they have been able to bind to another element is xenon. They got xenon to bond, I believe, with like 4 other carbon atoms, but it was like only for a split second, and it just kind of.
Yeah, because that's the only one that doesn't really line up. Like, it doesn't go by the. Like, all the other ones, are going by 8 sets of 8. So that they're, like, consistent +1, +2, like vertical lines.
Oh, I see.
Versus, like, that one, you go put a 2 in there for 52 and then multiply 8 times 6, you get 4 left over. So that's probably why they got it once.
Okay. So for the next diagram, I think I'm going to draw fluorine because that's got a -1 on the top. So where does that -1 come from? So fluorine has how many protons? 9 protons. And how many electrons? 9 electrons. Okay. So then I draw this out. 1, 2. Whoops. 3, 4, 5, 6, 7, 8, 9. Uh-oh. We don't have a full energy shell, so it's got a vacant spot open. It needs 1 more. Okay. So fluorine, for lack of better terms, will pretty much bind with anything. So I call it a horde, but whatever. And so like chlorine will pair up with, another fluorine or another chlorine. So it will gain an electron from another element, kind of steal it actually. So electron will come in, be transferred to fluorine, thus changing my number of electrons. Notice my protons don't change in any of this. If I do, then you've created alchemy here. But now look at my charge. I got 9 protons to 10 electrons. I'm more negative than positive. Okay, so it's actually a -1, and if you look at the periodic table, it's a -1.
So when all this happens, that's like when they're bonding, right?
Yes, which we haven't got to. I'm kind of jumping the gun, but I'm hoping you realize, wow, the periodic table is arranged in an awesome way to gain information. This is kind of a precursor to how atoms bond. Yes.
So the one is just the set of 4 is like that because it can add or subtract. That's why there's
Right, and that is why carbon is considered, it's got this amazing ability to bind with anything. It's got 4, it can form 4 bonds. Okay, so carbon is kind of like, that's why life is based here on carbon. That's why we're called carbon life forms. Now there is this kind of cheesy Star Trek episode, original Star Trek, where silicon, they found a new life form that's based on silicon. And the creature that's based on silicon kind of looks like a upside down pizza that you drop on a carpet, but it crawls on the floor. It's kind of weird looking, but it can think and whatever. So it's a silicon life form. But yeah, it's different. Okay, whatever. But brilliant at the time to think, hey, maybe what if there's other life forms based on silicon? Because silicon can also form 4 bonds. So brilliant in that way, but for the actual creature that they came up with, okay. Zoom.
What is that green stair-step line up there?
We call that the transition metal. So aluminum and silicon, they kind of have properties that are both metals and non-metals. So the elements that are along the transitions stair-step kind of share properties with it. And then you're probably going to ask me, what does the blue mean on my periodic table? So that means they're radioactive.
francium. That's the best.
Okay. Moving on. So that's atomic number, the number of protons. Now atomic mass is the number of protons plus the number of neutrons. Okay? In layman's terms, we tend to use mass and weight slightly differently, or actually like they're the same. I might say like weigh this, and you're actually recording the mass. But there is a difference between the terms mass and weight. So mass is the amount of substance. It does not change wherever you are in the universe. If I don't know what 72 kilograms would be, but if I weighed 72 kilograms on Earth and I went to the moon, I would weigh 72 kilograms. My weight on Earth, we use pounds, so I'll say, I weigh 145 pounds, but then if I go to the moon, I'm only going to weigh 1/6 of that. So going to the moon, because there's less gravitational forces, because the force of gravity has an effect on that, going to the moon would be a great weight loss program. Okay, so the atomic mass, like I just said, is the sum of the masses of its protons and neutrons. It's literally the number of protons plus the number of neutrons. Oh, shoot, I shouldn't have moved the camera because I want to go back to the periodic table. Ah! All right. Actually, I wonder if I have. No, I don't. Okay. Note to self. Next year, incorporate periodic table inside. But it's moving faster. All right, then I'm going to zoom. See how well this thing can zoom. Yeah, that's not bad. Okay. All right. So the atomic mass on my periodic table is this faded red number that you see on the top right-hand corner. So carbon has 12.01. Now, these numbers represent the average atomic mass because there are different forms of the same element in the universe. Okay, we call those isotopes. So like carbon has 3 isotopes, carbon 12, carbon 13, and carbon 14. And so what they do is they figure out the average of each, and then they add them up and divide by 3, so then giving you this average atomic mass. Now for simplicity, for carbon, let's just say I have a carbon atom that just has 12 as its atomic mass. So it's right here. I'm going to write something on my whiteboard.
What did you say those 3 carbons were?
Carbon 12, carbon 13, carbon 14. Okay. Everything's backwards. Okay. Atomic mass is number of protons plus number of neutrons. So P plus is protons, N with the 0 subscript neutral. Now, I just said carbon has an atomic mass of 12. Okay? Well, I already know how many protons it has. How many protons does carbon have? 6. So 12 equals 6 plus number of neutrons. Well, how many neutrons does this carbon 12 have? 6. So you can actually figure out missing pieces based on, maybe looking at the atomic mass, because you know what element you have, or vice versa. Maybe you don't know what element. Maybe you know the number of neutrons and the number of protons, so you can kind of figure it out from there. If I look at carbon 13, carbon 13. Well, the atomic mass is 13. I know that I have 6 protons. Well, now how many neutrons do I have? 7. Okay.
Does helium have any isotopes?
No, but hydrogen does.
Okay.
I don't think helium does. I know hydrogen does. Don't quote me on that.
It's just whether I gotta say this helium element or helium.
Okay. Yeah, hydrogen, I believe, has 3. Hydrogen 1, hydrogen 2, hydrogen 3, I think. All right, moving on to
So
the electrons.
isotopes is essentially the different atomic masses.
Right. And it's all based on the different number of neutrons, because they all have the same number of protons. Gosh, I went the wrong way. Okay, there. All right, moving on to electrons. So electrons, we just said, are located outside the nucleus, and they're actually located in regions called orbitals. And orbitals have different shapes. They can be dumbbell shaped or circular or donut shaped. But atoms with the same number of protons and electrons are neutral. And we've kind of walked through a few examples of that. Electrons are maintained in their orbital by attraction to their positively charged nucleus, but yet they don't crash into the nucleus. So we know that opposite charges attract. They are being held by the nucleus, but they have enough energy to be held away at a certain distance so it doesn't crash. Atoms in which the number of electrons is not equal to the number of protons are called ions. So, to the periodic table, those black numbers on the top, those are usually what charge those elements would be if they were ions. And an easy way to remember cations with anions. Cations means it has a positive charge, so group 1 and group 2 and group 13 with boron, aluminium, gallium, indium, and thallium. Those are all considered, cations. Cations are positive because you have more protons than electrons. So one way you can remember is that cation has a T in it, like a plus sign. Or you can say cats have paws. Positive. So, 2 ways to remember that. You choose which one. All right, anions have a negative charge, and that's because you have more electrons than protons. So, nitrogen, group 15, oxygen, column, group 16 and 17 with fluorine, chlorine, bromine, iodine, and arsenide. They usually form anion charges, or they're anions, I should say. I don't really know any fun ways to remember that anions are negative. It kind of looks like the word onion, and maybe kids don't like onions. So I guess that would be one way to help you remember.
Cations have more protons, and they're both constants. Anions and electrons are both vowels.
Oh, nice. Okay. So whenever you lose electrons, you become more positive because you have more protons. And whenever you gain electrons, obviously you become more negative and form anions. Now, when I was drawing the kind of electron diagrams on the whiteboard, and I had lithium, okay, because lithium had 2 in the first, and then 1 in the second, and it got rid of it. Well, you're going to get rid of that energy level, and now the cation is going to be smaller because it's only got the first energy level. So how big the ions are based on how many energy levels it has. So lithium here used to have 2. We got rid of it because it was unstable and it's easier to give that one up. And now it's a smaller ion. Chlorine had 7, okay, and then it gained 1, and now it's a lot bigger because now we have more electrons. Okay.
So the electrons are bigger.
Yep.
They're on the outside.
So this kind of ties into isotopes. All atoms of an element have the same number of protons, but they may not have the same number of neutrons. And so if you have different numbers of neutrons, but you're still dealing with the same element, now you're looking at isotopes. Most elements in nature exist as mixtures of different isotopes. Like I said, carbon's got 3 different isotopes: carbon 12, carbon 13, carbon 14. They all have the same number of protons. It's their number of neutrons that differ. Another example of an isotope would be chlorine 35 and chlorine 37. There are 2 isotopes for chlorine, and they exist, in a mix of in nature, I guess. Yeah. So here's another example of an isotope looking at oxygen. Oxygen has 3 different isotopes. Notice that the atomic number, which is the number of protons, stays the same. But my mass number changes. So this is the mass number, 16 for, so this is oxygen 16, oxygen 17, oxygen 18. They all have the same number of protons. So I can figure out how many neutrons each one of these isotopes have. So how many neutrons does this one have? 8. You took 16 minus 8 to get 8. How about this one? It's 9. 17 minus 8 is 9. And for oxygen 18? 10. 18 minus 8 is 10. Any questions with isotopes, atomic mass, and atomic number? All right, we're going to look at one more example of an isotope, and I've mentioned it before, carbon isotope. Now, like I said on the periodic table, it existed as 12.01. Okay, it's close to a whole number, and so that 0.01 is telling a story here. If it's 12.01, that means there are a lot more carbon-12 isotopes than there are carbon-13 and carbon-14. This one kind of shows the math a little bit. 99% of carbon-12 isotopes in nature, followed by carbon-13, and then the most rare is carbon-14. Carbon-14 is really, really unstable, tends to break up into lower atomic numbers. But 99% of all carbon you find is carbon-12. And so as a result, your average mass will be closer to 12.
So is a Dalton, is that like a subatomic particle or what?
A Dalton is just like 1.
Yeah, like your
Yeah, it's protons and neutrons, because protons and neutrons tend to have the same mass. Electrons.
The number of Daltons will just be the same as the
What's
atomic
a Dalton?
mass.
It's named after John Dalton, and
It's a unit.
it's just a unit for mass. So I know we've been counting. Oh, oxygen 18. The atomic mass is 18. Well, I really should be saying 18 Daltons.
Yeah, so it's just the same.
So if you look at the periodic table, I know you can't see this, but chlorine has an atomic mass, average atomic mass of 35.445. And I just told you that chlorine has 2 isotopes, chlorine 35 and chlorine 37. Which isotope is more abundant? 35, because the average number is closer to 35 than it is to, 35.45 is closer to 35. So here's a diagram showing the isotopes of carbon with carbon-12, and you notice that they have the same number of protons and neutrons. You add them all up, you get 12. And then here we have one more number of neutrons compared to protons, and then 2 more.
So even though the protons and neutrons are the same in carbon-12, it's still considered isotopes.
Yep. Yeah, because it's carbon-12.
Oh, so like all atoms have minimum of 1, other than hydrogen.
What do you mean?
Like all
Minimum
atoms
of
have
1.
at least 1 isotope, because is that just like the base?
Don't they all have like
We just, you know what? I don't know how to answer that, because I know hydrogen's got a couple different forms, and I honestly don't know if helium has an isotope. And I feel like I should know that, but I don't.
Well, I just thought you meant like because carbon-12 has 6 protons and 6 neutrons, and say like helium has 2 protons and 2 neutrons, is that in itself just considered a form like a
Okay, segueing back to our little story of chemical evolution hypothesis. So geologists and astronomers can estimate when all those events, like how Earth formed, or how long ago it formed, using a procedure called radiometric dating, because atoms that are unstable tend to break down into something that's more stable, and as a result, they may emit radiation or a particle. So we call these radioactive isotopes. A lot of times they are blue on my periodic table. That means they're radioactive. So you may know that like uranium will break down into something more stable. It will literally change into a different element. Okay. So the original isotope, we call it the parent, and then whatever it decays into, we call that the daughter. So we call this radioactive decay, this ability to go from the parent atom to maybe to a different isotope or a different element. So radioactive decay is a super important feature because basically you look at the proportion of parent to daughter, and the breakdown time is constant. And a good thing about a radiometric decay is it's kind of like a clock. You can work backwards and kind of figure out how many half-lives have passed, which is the time it takes from the parent to decay to the daughter isotope, and give you an approximation of how old whatever it is you're looking at is. So uranium-235 decays into lead-207, and to do this, the half-life is 713 million years. So then we can find rocks or samples or whatever and work backwards, give an approximate age of that. So this diagram, I think, does a nice job kind of graphing the half-life of, it looks like potassium here. Get this nice little curve, exponential curve, telling you half-lives, so in billions of years. So like I said, it has many useful applications. A lot of times you can take a specific molecule in a sample, follow its fate, or figure out what it does in a chemical reaction. So like I told you the story about the circadian rhythm with PP5, the gummy bear, bind into mCry, and we were like little minions for my professor. We actually had to take our molecule cry with radioactive dye, and then look at it underneath a very expensive microscope, $250,000 microscope, and it would emit very bright neon colors. So we tagged it with 3 different colors, green, blue, red. And I think what we were looking for, we tagged it red. Blue usually is the nucleus, and then green is the cellular, or the cell membrane. So we were looking to see where red was. Was red inside the cell? Was it in the nucleus, or did it get outside the cell? So yeah, that's how we figured out whether or not it binded to PP5 or not. So it's kind of cool. Downside to this, it can damage living cells. So with our experiment, it was very tedious because we were coming up with a new procedure. So we had many trial and errors before we figured it out. Can produce mutations and even cause cell death with this radioactive tag. So.
Why you don't want to stand around.
All right, how old is Earth? So we can use radiometric data to determine when rock formed. And so geologists have to estimate 2 quantities. First off, the relative amounts of the parent and daughter isotopes in the rock sample, and then the relative amounts of the parent and daughter isotopes that existed when the sample formed. So this is usually estimated. Okay, so that's why it's not exact, but it's an approximation. We do have some really old rocks. Like one of the oldest is found in Australia. There's another really old rock in Africa, and there is another extremely old rock right here in Minnesota. You may not know that. It's off Granite Falls. I think you have to take, is it Highway 7 that leaves Granite Falls? But there's like this, like the first gravel road you take, and there's this huge granite outcrop.
Can I have your attention for the
Well, we'll
announcements,
just pick
please?
it up there.
Seniors are thinking of taking the ACT